this is this is going to be your one of the most important lectures for this particular chapter, rotation, motion about fixed axis. Am I audible properly, clearly, everyone? Okay, so what we were going to discuss in this lecture, kinetic energy, or you can say rotational kinetic energy, and the acceleration and the time, and you can say displacement whenever a rolling motion is going to be done. What is a rolling motion all about, or what is the acceleration whenever any particular rigid body is going to be dropped from an inclined plane. Is this clear? So these are the important subtopics we are going to discuss in this particular lecture. So I don't think so we need to wait, but just for a second, because this camera is little bit tilted and the AC is not working, so I need to do the both of them. Just stay there and read this first page. Okay, this is the recall for this particular class live session. Angular moment we already discussed, so read this. I'm just coming in a minute. Hello, hello, hello. I tilted. More. Now perfect, right? Am I audible, visible clearly to each and everyone here? Yes, sir. Just a minute. I think it's perfect now. I don't need to waste much time in this. Already we have, spent 7 minutes. Okay, so good evening, everyone. And this is going to be your important lecture. In this particular lecture, we are going to discuss about what? We are going to discuss about the rolling, or you can say kinetic energy of a rotation motion. Is this clear, everyone? Clear? Okay, so let's start this thing. Angular momentum. We already done this particular thing. Angular momentum, the momentum of a linear momentum of a moving particle with respect to axis of its rotation is known as angular momentum. It can be represented with the symbol L or with the symbol J all together, and that is nothing but R. That is nothing but R cross P. R is the perpendicular distance from the axis of rotation. I myself look little in this way. I need to rotate them. Yeah, perfect now. I think I don't need to do anything. Yeah. So it is a vector quantity which is often represented by symbol L or J. It is an axial vector, always perpendicular to the plane of motion, and angular momentum J equals to R cross P, or you can write with the symbol L. Okay. Putting the value of P, which is M cross V, M R cross V, because mass is a scalar term, R cross V, and that is J R P sine theta N. This sine theta N gives the direction of what? Gives the direction of J or N. Okay, whatever the symbol you can pick it up. Means basically this N vector gives the direction of my angular momentum. Theta is the angle between R and V, and N is a unit vector perpendicular to plane of R and V. Basically, the direction of L is going to be perpendicular to both R and V, and that is the, you can say, that is we get from the vector law or vector product of three vectors. Okay, and that is all about, again, the simultaneously what it looks like. The direction of angular momentum is perpendicular to plane of R, V, and it is given by the right hand screw rule. We discussed this thing in a great detail, so I'm not going to discuss again and again. If theta equals to 0 degree, A area is going to be pi r square theta, and J is going to be 0 minimum. For theta equals to 90 degree, J is going to be MVR, because J, or you can write L, I choose both, both the symbol MVR sine theta. Okay, so using this particular thing, sine theta is 0 at 0 degree, sine theta is maximum at 90 degree. So using this, that is the minimum, that is the maximum. SI unit of J is joule into second, same as the Planck constant. And you can say dimension is M1 L2 T minus 2. Okay, so we done this thing in previous classes. So that is something new for you. Even I put it this thing in a you can say radius recall, but it is new, and more than the new thing, it is important. Okay, simply what it is, first of all, see, in the previous lecture we talk about MOI basically. MOI stands for moment of inertia for different objects, for different bodies. In general sense, if I'm going to write the moment of inertia, so beta I can write moment of inertia I equals to mass of a body, any particular kind of a body, and k square. So this k square is basically the radius of gyration. Is this clear, everyone? It is a general terminology for writing the moment of inertia. Is this clear? So we are going to compare and we are going to find the radius of gyration for different objects. For simplest thing, like the radius for disk. Okay, for solid disk, even I don't put the disk example here. For solid disk, I is going to be 1 by 2 mr square. And if I'm going to compare this general formula for not this, if I'm going to compare this general formula with to find the radius of gyration, this general formula A with this formula B. Okay, with this particular formula, with this formula B, and this is what for disk. Okay, for disk we have this. So comparing A and B, the left hand side is going to be equal. So the radius of gyration for disk, what it is going to be? But the radius of gyration for disk, radius of gyration, radius of gyration for disk. If the left hand side of equation A and B is going to be equal, so automatically the right hand side is going to be. So that is nothing but mk square equals to mr square by 2. Going to be cancel out, and then k is nothing but r by root 2. K is going to be nothing but r by root 2. And this r by root 2 is the radius of gyration for what? For disk. Is this clear, everyone? So basically what it is a general, you can say perpendicular distance for a general, you can say it is a general perpendicular distance to find the moment of inertia, this. Okay, clear, everyone? And you can say this particular, what it is written over in definition wise, it is the distance whose square when multiplied with the mass of the body gives the moment of inertia of the body about the given axis from any given axis. For a body of mass m, if k is the radius of gyration, then I equals to mk square. So in the same sense, the you can say reverse words or reverse language, it is written over here. It is the distance. It is the distance from the axis. Okay, it is the distance from the axis. So when I multiply or when I square this distance and multiply with this mass of any particular shape or of any particular kind of rigid body, so I can get the moment of inertia. Is this clear? So in general, k is nothing but under root of Im. From this formula, from even formula number A, what we can get, beta? K is nothing but I upon M. So if we know the I for any particular kind of body, or you can say for different shape and size of body, so we can find the K. Through this concept, a real body, particularly irregular, is replaced by a point mass for dealing its rotational motion. Example, in case of a solid sphere rotating about an axis through its center. So the I of this particular thing is 2 by 5 mr square. Is this clear? In the previous lecture, we find this, the moment of inertia for solid sphere. Okay, where I can write, okay, here I can write in this box, I for solid sphere, that is going to be 2 by 5 mr square. Okay. So comparing this, I equals to k equals to under root I by m, putting the value of I, we can get, sir, I am having problem with my camera, I will try to solve it. It's okay, better. So k is going to be there, I mean the radius of gyration for solid is r, because it is a square thing, under root 2 by 5. Okay, under root 2 by 5. The same thing which is written over here. Clear? So for any irregular shape or for any regular or symmetric shape, we can find the radius of gyration, and sometimes a simple direct question for any particular system of body. What is a system bodies? Like there is a square. Okay, what I am saying right now, just give me a minute. Yeah, suppose there is a square, and with this square there are going to be attached this kind of, not this, wait. With this square, suppose you have 4 semicircles in this. Okay, 4 semicircles in this way. Obviously, it not look like symmetric, but obviously they are symmetric. Why so? Because the diameter of each semicircle is same. So it is not look like symmetric because of my drawing capability. So don't judge on behalf of that. And this is the axis of rotation, right? So on this axis of rotation, if I am going to say, first of all, find the moment of inertia. So moment of inertia is nothing but half sphere. You can say semicircle. There are 2 hemisphere, one hemisphere, another hemisphere, another hemisphere. So there are basically 2 spheres and 1 plate. So when you combine that, you can get the total moment of inertia, that is moment of inertia for a square plate, or you can say rectangular plate. Okay, rectangular plate. Suppose rectangular plate have dimension b and a, and automatically then radius r is going to be b by 2, isn't it? You can see that from this diagram, because it is a diameter. So diameter of this particular semicircles or hemisphere. So radius of hemisphere is going to be b by 2. So this is going to be I1. I is going to be I1 plus I2. And I2 beta is going to be the moment of inertia, the MOI, moment of inertia for 4 hemisphere, right? And once you find the total moment of inertia, then total moment of inertia can be correlated with this I equals to mk square. Okay, and when you find this, so automatically with this formula, k under root I by m. Okay, suppose each particular mass, suppose each particular different shapes even have a symmetric mass m. Clear, everyone? So this is how a simple question can be converted into the complex or typical one. Is this clear? Simple concept. What is the radius of gyration? Radius of gyration is nothing but a distance whose multiple, or you can say whose square and product with the mass can give you moment of inertia. So for different shapes, we can find the radius of gyration for different simple shape, irregular shape, or system of shapes. Is this clear, everyone? Is this clear now, everyone? Should I move ahead? If it is clear, so. Everyone. Clear na? Bhuvana, Nitra, Kanishka, Ashwin, Karthik, and Mokeshwaram, and Anushika also. Okay, if it is clear, this one, yeah. So that is, we just simply write. So instead of solid sphere, we can assume a point of mass m at a distance r under root 2 by 5 from the axis of rotation for dealing the rotational motion of the solid sphere. Means instead of saying solid sphere, we can say that there is a point mass particle of mass m, and the distance from this particular point mass particle is radius of gyration is this r 2 by 5 under root, or under root 2 by 5. Is this clear, everyone? Clear na? Moving ahead, this is important one also. what it is? Radius of gyration, or you can say the slope in between log of I, and that is net 10g, that is log of k. The log I and the log k gives you this particular thing, means a little bit complement, or you can say what it is, this mx equals to y plus c. So this is always going to be there. The radius is the radius of gyration, and you can say the log of that. Sometimes this direct curve they can give you, like what particular this curve is related for. So that is nothing you can say much about it, but it is just gives you the direct relationship between log of I between the log of k, where k is the radius of gyration, because at that time most of the student doesn't know what k is. Okay, so k depends on first axis of rotation, distribution of a mass of a body, and k doesn't depend on what? Ground mass of the body, that is position of the body, on all angular physical quantity. Why so? Because k, as we know, nothing but I upon m. Okay, where I depend on the two things. If you change the axis, or if you change the symmetry of a body or distribution of a body. Like for discrete, we have a different kind of moment of inertia. For continuous, we have a different kind of moment of inertia. Is this clear now, everyone? Okay, so radius of gyration does not depend on the mass of the rigid body. Graphical relation between log k and log I is like this. Initially, even at the 0 point, you can get the log I if you put the log of k is 0. That is the thing. Okay. Now in the next slides, we are going to see the important diagrams, or you can say points, about the dynamics of a rotational motion about a fixed axis. So moving ahead, see, these are the next two slides even, basically the different real life example in which the axis of a rotation is going to be fixed, and the human, or you can say, and the person and the body is going to rotate about a fixed axis. Is this clear, everyone? And you are going to see the physical significance or the real life example through these given points. Is this clear now, everyone? Clear? If I'm asking it is clear, so please write it down, because I cannot see your faces every time. So just after seeing your faces, I cannot get, is this clear in your head or not? Because only two persons' face is visible on the this particular slide. And one of them, Mokeshwaram, is not opening his camera. Right now he opened his camera. Okay. Yeah. In this way, just write yes or clear. And if you have any particular doubt, so you can ask me out in between also. Got it? So dynamics of a rotational motion about a fixed axis. That is, first, a man with his arms outstretched and holding heavy dumbbells in each hand is standing at the center of a rotating table. When the man pulls his arms, the speed of rotation of the table increases. Okay. The reason is that on pulling the arms, the distance r of the dumbbells from the axis of rotation decreases, and so the moment of inertia decreases. Therefore, by the conservation of law of angular momentum, we have this formula L can I, also represented with I omega. Okay, this is one of the formula also. I can be treated as a mr square, and automatically we can get mvr all over. Why so? Because I is nothing but mr square, or omega is nothing but v by r. So putting the value all together, I, which is, you can say, angular momentum, which is mvr, okay, which is mvr, we can put in this way also. So when this particular man, you can say, stretch his hands, so r is going to be increases, and when r is going to be increases, so automatically this I is going to be increases, but omega is going to be decreases, because for omega r is inversely proportional, and for moment of inertia r square is directly proportional. Sorry for the late. Okay, beta. So that is, means when there is no angular force, or you can say when there is no torque, So we have this formula also from the previous classes. Torque tau equals to del L by del T, which is going to be 0. Okay, even for constant, you can say angular momentum, and that is angular momentum conservation. When we don't have any external torque, so it is rotating on its own, so we don't apply any particular torque. So in rotating about this particular fixed axis in the rotating table, L can be represented as I omega. So when the man is going to open his hands or arms, so I is going to be increases, omega is going to be decreases. In reverse case, if he closes his arms, so omega, which is angular speed, is going to be increases, and I is going to be decreases. Is this clear, everyone? And that is what it is written over here. Clear now, everyone? Clear, beta? Should I move ahead? Okay. In the next slide also we are going to see something. You can say look-alike thing. Look-alike means whenever you can say a swimmer is going to jump from the spinning board. So the axis of rotation is going to be there. What? Air or what? The spinning board. Because the spinning board is taken as an axis, and from that spinning board, the swimmer is going to be jump in this way, and it is going to rotate, 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 and then boom, boom into the, jump into the swimming pool. So that is how in real life also, when a driver jumps into the water from a height, he does not keep his body straight, but pulls in pulls in his arms and legs towards the center of his body. On doing so, the moment of inertia I of his body decreases, but since angular momentum, which is I omega, okay, this, keep this thing in your mind. L equals to J equals to I omega. So what everyone is going to, why they close their body, wrap their body to increase their angular velocity, to increase this omega, because there is no external torque which is going to change this L. So L is going to be remain constant. So if they, instead of in this shape, as you can see in this shape, the R, because I is nothing but mr square, mass of a person is going to be remain same. In this, if it is taken as a center of a human, so this is R increases, here it is also a little bit decreases, but here in this case, as you can see, R is very less. Clear? If R is very less, means the perpendicular distance, the axis of along the from the, you can say the perpendicular distance from the axis of rotation, which we can take the center point of a human, this particular you can say line. So obviously I is going to be, then obviously I is going to be decreases. Okay, and if I is going to be decreases, so to make this thing constant, to make this equation 1 or A constant, omega needs to be increases, and that is what it is written over there. His angular velocity omega correspondingly increases, hence during jumping he can rotate his body in the air. So that is why they are able to rotate their body easily. Clear? Everywhere here also we can see the rotation of a human body just because of this simple thing, because there is no external torque. If there is no external torque, so L, because torque is 0, so dl by dt is 0, means angular momentum is going to be constant, and angular momentum is related to the I into omega. So the moment of inertia of a human body is going to be decreases, because human can squeeze its body, and the radius from the perpendicular axis is going to be squeezed. So when it is going to be squeezed, or it is going to be lesser, so the I is going to be lesser, and to make this L constant, angular momentum constant, omega is going to be automatically increased. Clear, everyone? That is the concept. Clear now? In day-to-day life also. The same concept is here as well. We can see that in the same way, the ice skater and ballet dancer increases or decreases the angular velocity of a spin about a vertical axis by pulling or extending out their limbs. Okay, in pulling, when they are, when they increases their hand in this way, so again, this is, you can take as a axis of rotation, the human central part. In this, R is going to be increases in this case, right? So R increases, I increases, omega decreases. Omega is what? Angular velocity. Okay, just this formula. And in this case, R decreases. Okay, automatically I decreases and then omega increases. So I skater and valid answer deliberately you can say close and wrap up their arms to increase or decrease their angular velocity. Clear now everyone? These are the basic where we will use this thing to see the increase and decrease in the angular velocity. Here as well, axis is horizontal angular momentum, about the vertical axis is 0, about the vertical axis is going to be 0, and axis is vertical, if angular momentum about the vertical axis is still 0, man and chair is spin in direction opposite to the spin of the wheel. Means if this particular wheel is going to be rotated in this direction, okay, into the plane of paper in this direction, so it is, this particular man and this particular rotating chair is going to spin in opposite direction to make the balance of our angular momentum of this particular spin and of this rotation. Okay, if it is moving in this direction, so then wait a minute. If it is moving or rotating in this direction to make this constant, it is in opposite direction, angular momentum of a man and this particular table. Okay, simple thing in each cases, L is constant. Why it is constant? Because we don't apply any external force, rotational force. Clear na? Like there is simple one thing, until unless there is no external force, so F, which is rate of change of momentum del P by del T, is going to be 0. And when this scenario is going to be C, so del P is 0, and this thing states us, this thing gives us, what it gives us? What it gives us? P is constant. Clear? In a same sense, we are seeing the day-to-day life examples in the same scenario. What I am writing since last 2-3 slides, torque tau, which is dl by dt, is 0 because there is no external torque. So when dl by dt is 0, so automatically time is changing. Okay, time cannot stop for anyone, for anything also. So dl is 0, that it states that L, which is angular momentum, remain constant. And here we represent L with I into omega. So in different cases, I is related to the R, which is perpendicular distance. So if we extended our arms, if we are closing our arms, so basically we are increasing or decreasing the R, which is perpendicular distance. And in doing so, what we were doing in generally, moment of inertia is increases, so omega decreases, omega increases, so moment of inertia decreases. Clear now everyone? Why? Because this quantity is constant. As simple as that. Okay, and even I write it down here. Clear now everyone? If you have doubts, question, query till now, you can ask. Next page you can read out. That is related to the previous, you can say, diagrams. Okay, so the angular velocity of a planet around the sun increases when it comes near the sun. When a planet revolving around the sun in an elliptical orbit comes near the sun, the moment of inertia of the planet about the sun decreases. In order to conserve angular momentum, the angular velocity shall increases. Similarly, when the planet is away from the sun, there is a decrease in the angular velocity. What it is in general, we know Earth is rotating around the sun in an elliptical orbit. Okay, so when Earth is near to the sun, so R is less. R is less means moment of inertia is less. R, because sun is taken as a axis. Around the sun is revolving na. So I is going to be lesser. Why so? Okay. One last thing I'm going to teach you in this way. Don't worry. This is your elliptical orbit. In this elliptical orbit, we have sun here. Just a minute. We have sun here at one corner, or you can say a little bit there. Yeah. And suppose this is the planet Earth. Okay. So when this particular planet Earth is at particular position A and at particular position B, now you can understand more clearly. So at B and at A, as you can see clearly, if I take sun as an axis of rotation, and I need to because Earth is rotating around the sun now. So at this particular case, you can directly see this here R is minimum. Clear? Here R is minimum, and I can write R capital. Here R is maximum. So automatically at B, R is maximum. And when R is maximum, I, which is M R square maximum. So omega is minimum. Why so? L, which is I omega, is constant here as well. In the next chapter, even we are going to learn in a more rigorous way using the Kepler's second law. Like aerial velocity is going to be constant, and that is L upon 2m is a constant. Mass is constant, so automatically L is going to be constant. Clear? For, or you can say at another position. What is another position beta here? At particular position A. At A, R is minimum. Clear? When R is minimum, so obviously I, which is M R square, is going to be minimum. And whenever it is going to be minimum, so automatically omega, the angular velocity, is going to be maximum. Clear, everyone? So that is all written over there in the first paragraph. Nothing more than that. Means at particular position A, the Earth revolves around a sun with a higher velocity, and here it is revolved with a lower velocity. Omega prime high, omega less. You can write prime. Clear, everyone? That is what it is. The speed of inner layer of wind, while wind in a tornado is alarming high. In a tornado, the moment of inertia of air will go on decreases as the air moves towards the center. So, sorry, the same thing is written over here. Just take an example as a tornado in your head. Okay. So tornado is something look like a V or cone shape. So in V or cone shape, if I am going to inside or at the center, or you can say near to the axis of a rotation, so R is less, I is going to be less, and then omega is going to be high. In a similar way, at the farthest point, at the, you can say, circumference of this tornado, R is high, moment of inertia is high, omega is less. Clear na? You guys sitting like this, you never ever seen a Tom and Jerry or a tornado in there. So whenever a tornado is passing through any particular, you can say home, so that home is going to be blown up from the center, not from the, you can say, outer surfaces. Because at the center, the tornado is very powerful. Why powerful? This is the science, this is the concept behind that. Okay. And if you don't understand what it is, after just this class or even in between the break, YouTube what a tornado is. Here in coastal areas, you can see the tornadoes, or you can say tsunami and high altitude or fast moving winds. Basically, in western coastal, I'm saying, sorry, in western country, specifically in Florida or in USA, in New Zealand also, you can usually see the tornadoes at least once or twice in a year. Clear? Because they are very, very near to the sea, and they are in west part of the country. I mean, not country, Earth. Now, the next thing is going to be important. We see so many examples from day-to-day life taking this L equals to I omega constant. Now, we are done with this. Okay. Now, this is very, very important again. Even easy one also. Okay, let's do this quickly, and then I'm going to give you a break, because I think you need a break before the main thing. Even the main thing is not started yet, the rolling motion, and you are seeing like Sir, how much you are going to teach us in today's 2 hour lecture? I don't started yet. And seeing Kanishka is like, oh my goodness, the main topic is not started yet. So how I'm going to grasp that much topics, right? Have it up. Is this going in your mind? Kanishka, I'm asking to you. You all like, so I mean, sorry, you all of them look so tired. What you guys doing since morning? I want to know personally. It's 8 o'clock. At 8 o'clock is my time in my school time when I don't see any particular book after 8 o'clock. Yeah, at 12, at 11:30, I start again. What you guys are doing since morning? Means morning after school or from the school time. I want to know personally. Anyone, go ahead. I need to shift a little bit direction because in this way I can't teach you. Seeing so boring and sleepy faces like you. Tell me anyone, at what time from your school you are free today and why are you so lazy? I mean, look sleepy and lazy altogether. Because I leave my bed today at 6:30 morning. Last, DRT saying something. Go ahead. Speak up with the mic. Whosoever going to say anything. Don't write it up. Tell me with anyone. You can share. I share na. I wake up today at 6:30 and sleep at 1:30 last night. Until then, I'm working also. No, I'm not look energetic. I know this. I want to know your, uh, you can say, not agenda, but your. Hello, hello, hello. Am I audible? Yeah, so I'm saying the next thing is going to be a very, very important thing, and you need to wake up from your sleepy mode. So I want to know, is this general thing for you guys, or you did a lot of hard work something today? Every student, I am asking. Tell me something. Or your school examination and something and so going on. Okay, tell me how many of you, girls or boys, anyone, you can say participate in home chorus. Chorus means any work which is going to be done in your home. Cleaning, mopping, washing the utensils, making a tea even. Don't say, sir, I cook Maggie for myself. Don't say this. Cooking Maggie for yourself is nothing a home chorus thing. I want to know personally. At least you can write this about it. How many of you know something which is done in your home or you are not doing anything? Because at your age, I started making tea for myself at least. Because I have a habit. I mean, I'm a night owl. What is a night owl person? A person which, a person who likes to wake up late in the night. So obviously, if I'm waking late in the nights, so I love to drink tea more often. So I learn a bit early in my life how to make good tea at least. So no one going to be bothered after 12 a.m. I'm talking. Tell me, how many of you know? All or none of them? Arey bhai sir. None of them you know something. Oh my goodness. Anushka said no, sir. What about you, Netra, Bhuvana, Mokeshwaram, Kanishka, and this Pranav or DRT? None of them you don't know. I mean, you know anything. Something. Gardening maybe. Gardening can be taken as a home chorus also if someone loves gardening. Or mopping or cleaning. But you are born in so good time then. My mom scolded me so much about it. You are being, I mean, when I was in my class 12th, even in class 10th, I started doing like this. What I'm asking to you. Okay, it's okay if you are not doing so. Lucky ones. So back to the topic. Like we after this particular slide, we are going to talk about everything, or you can say specifically kinematics of a rotational motion about a fixed axis. Means if any particular body is going to rotate about a axis, so the work done, the potential, no, potential differences sticking in my head. So the work done, power and kinetic energy of a rotation, and then work energy theorem also. And then I'm going to give you a break, smaller one, and then we are going to start the rolling. Okay, so let's quickly do this. So when our body, as we know, see simply the every basic concept is going to be used again and again. You don't need to learn anything new. We know work done. What is work done? Force into displacement, right? Is this clear? F dot D, and that is a scalar quantity. Okay. In a same sense, if I'm going to talk about for the rotational case, so for a rotational case, work done is torque tau into theta, because here the force, or you can say the rotational force is torque tau and the displacement is theta. Simple as that. So when a body rotates under the action of a torque, when the work is done by the torque, if tau is uniform and rotates by an angle theta, then the work done is going to be T, or you can say tau theta. But if tau does depends on theta, for example, in case twisting a wire, T equals to C theta. What it is? Say twisting is, suppose there is a wire, if I'm going to twist it. So there is a constant which is C, and the moment I release this, so it is going to revolve. Got it? So that is your torque tau directly proportional to theta, and torque tau is C theta. This proportionality constant C is a constant for different material. It is known as twisting constant. Twist, or you can say twisting constant, depend on the material. For example, spring and you can say wire have a different case. Clear everyone? Where C is a constant. So work done dW is going to be T. D theta means just a little bit theta change, and what amount of work done you need to do. So that is your small amount of work done in twisting in a very small angle, that is d theta. Since variable tau, we know T is variable, so W, which is going to be T d theta integration, and this theta is going to be 0 to theta. 0 means whatever the plane angle, whatever the you can say angle 0, and then from you can say 0 angle to any particular theta we are going to rotate. So integration from 0 to theta, C theta d theta, is gives you C theta square by 2. And then what it is? It is the work done in twisting or in rotating a wire from theta 1 to theta 2, or you can say from 0 to theta angle. Clear? Is this clear everyone? We just doing this integration, nothing more. 0 to theta, C theta d theta. So C is constant, theta to the power 1. So it becomes theta square by 2, this equation. And that equation is, you can write equation number 1, very important. Clear? So that is from 0 to any particular theta. Now I want to twist, for twisting of a wire for angle theta 1 to theta 2. So the limit now, or you can say this dW, which is W, is going to be theta 1 to theta 2. And dW from this relation is going to be theta 1 to theta 2, C theta d theta, and that is going to be nothing but C by 2 theta 2 square minus theta 1 square. Clear? And that is also an important scenario. And equation number 2. Clear everyone? And we know in any particular conservative kind of force, you can say whenever a particle is rotating in a circle or rotating around a axis, so it is a conservative force. What is a conservative force? In which the work done is not dependent on the path. It is only and only dependent on the initial and final position. So this work done can be stored as an energy. So kinetic energy of a rotation. The energy due to rotation, okay, not this color. The energy due to rotation of a motion of a body is known as rotational kinetic energy. The I, if I be the moment of inertia of a body about axis of rotation and omega is its angular velocity. So kinetic energy of rotation is half I omega square. Okay, and that is nothing but if I'm going to kinetic energy, if I'm going to use simple formula, na, KE is going to be half mv square, right? Multiply and divide with the r square because omega is v by r, right? So if I'm square and square, basically I'm doing the multiplication of 1. Clear? Multiply and divide with the r square. So v square upon r square gives me omega square and mr square gives me I. The same thing. Clear? I can put I mk square, radius of gyration, in the form of radiation of gyration. So this one is the important relation altogether. And this is my equation number 3rd. I can put I omega as a j also because I omega is j. Clear? So I can put this also. J square upon 2i. Why so? Because I omega is j. If I'm going to do this, so that is basically j square. That is basically j square. So I can write j square by I also. Clear na? So rotational energy in different formats I'm going to write. And right now you see everything is very easy, but beta whenever it is going to ask in question na, and you don't have any other thing other than j, omega and so, then you're going to find a little bit difficulty. So understand here, we write these all things and all this equation 3, 4, 2, every particular equation is important here. Clear beta? Whatever the boxes I'm writing for you, everything is important. So that is your equation number 5th. So basically, I can write in any kind of format. The basic thing is kinetic energy is the energy due to the motion, but here we talk about the rotational motion, nothing more than that. Clear? Okay, just one more and then I'm going to give a break. Now, I rewrite the formulas. Okay, kinetic energy of rotation is 1 by 2 I omega square, if I'm not wrong, 1 by 2 I into j square, or yeah, simple these formula. Okay, so if omega is constant means if omega is not changing, kinetic energy or rotational kinetic energy directly proportional to I. In the same sense, if I is constant, or you can say if moment of inertia is constant, so ER is basically kinetic energy, or you can say rotational kinetic energy is directly proportional to omega square. And if this particular J is constant, so ER is inversely proportional to this. So just using this, and what it is the rotational kinetic energy in different form, nothing more than that. Rotational kinetic energy, or you can say kinetic energy of a body in the rotation. Work energy theorem, same thing. Like we know the work energy theorem, it states that work done can be stated as a change in kinetic energy. So here also we can define work done by torque. Okay, I'm going to write in this way, is nothing but change in rotational kinetic energy. Change in rotational kinetic energy, and that is 1 by 2 I omega 2 square minus omega 1 square. Means if my body, if an object, not my body, if an object is if an object is initially rotating with omega 1, and after some time, or you can say after getting higher angular speed, it starts rotating omega 2. So the work done due to the torque tau is nothing but change in rotational kinetic energy, and that is 1 by 2 I omega 2 square minus omega 1 square. Clear? Same thing I'm rewriting for rotational motion, for an object, for a body rotating around an axis. Nothing I'm changing. What we learned in the previous chapter, WEP, WEP stands for work energy theorem. WEP stands for work energy power. So whatever I learn in the WEP chapter, work energy power, like kinetic energy for translation motion, rotational kinetic energy. Work energy theorem for translation motion, work energy theorem for this particular thing. In the next slide, we are going to talk about what? Power. So rotational power, even I give you this in the previous lectures also, but still, rotational power, P rotational is rate of change of kinetic energy or rotational energy, d by dt r, and d by dt of j dot j by 2i. So when we are doing this, so basically we can get this relation back altogether. Important one, sixth. Okay. From the following, this is your sixth equation. So let's take a break for 5 minutes, or you can say 5 to 10 minutes. And then after 5 to 10 minutes, we are going to talk about rolling motion. That is important. A little bit more important. Clear? So from the beginning of this live session, what we've done, like what is radius of gyration and what is the graph between radius of gyration and log of I, and the different day-to-day life example in which angular momentum is remain constant, but I and omega can change simultaneously. And then the rotational kinetic energy, and you can say rotational kinetic energy in different forms, work energy theorem for rotation motion, and then power for rotation. Torque tau into omega. This is the same formula which we have, power equals to force into velocity. Here in rotation, this is translation, and that is rotation. Clear? And how we can get? Nothing but power is rate of change of energy, or you can say time, work. So put that is F dot D divided by T. F is remains same, F, and D by T is velocity. Nothing I am doing new here. Just I am rewriting, I am representing everything into the terminology in the form of what? Rotation. Clear now everyone? Good. So let's take a break for 5 to 10 minutes. Not more than that. Hello, 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 hello. Am I audible? Beta, hello. Are you there? Hello, 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 hello. Hello, hello, hello. Hello, am I audible? Hello, hello, hello. Hello, 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 hello. Am I audible? Okay. Yes, yes. Okay. So, just, is this clear now till now? Everything clear? Everyone? We go through the real life example and what is radius of gyration and just angular momentum thing and kinetic energy in rotation and work done in rotation and power in rotation. That is simply thing we done till now. The next thing is going to be simple as well, but what it is rolling motion. See, rolling motion you can understand or you can see in your day-to-day life. Every particular automobile or every particular motion, rotation and translation motion is combined. Okay, if a wheel of a, you can say of a tire, or you can say if any particular kind of wheel is rotating as well as translating from particular position A to any particular position B on the ground, so that is a rolling motion. Why so? Because, okay, that is very simple to understand. This wheel or you can say tire have a center, so it is going to rotate, okay, in this way, isn't it? And meanwhile they are do the translation motion as well. They are traveling, or you can say translate, from this particular initial position, which is position A, to position B. Is this clear, everyone? Motion or translation motion as well as the rotational motion is known as important one, rolling motion. This one is important. It is known as rolling motion. Clear, everyone? Is this clear, everyone? Means the combined translational plus rotational motion is known as rolling motion. Or a rolling motion is a special case in which an object is rotating around an axis as well as it is translating from one point to another point. Clear? So in case of a rotational motion of a body about a fixed axis is called a spinning axis. As you can see, there is always a center point in each particular wheel, in each particular tire, and that center is attached to the axle of a, you can say, chain, or you can say axis, and that is going to rotate. And along with the rotate, they are traveling, or you can say they are transporting, they are doing the translation motion from one point to another point also. So if in case of rotation, motion of a body about a fixed axis called the spinning, axis of rotation also moves, the motion is called combined translatory and rotatory motion, that is known as rolling motion. Most of the what happened to me today? Most of the rolling wheels and flying saucer can be example of this type of motion. Flying saucer is whenever any particular footballer or a saucer player, kind of a same like a football, kick the ball, so that particular ball doing the rotational motion as well as the translation motion. Clear, everyone? So obviously, if any particular object doing both kind of motion, so the kinetic energy is going to be total, and that is going to be the total kinetic energy. Is this clear, everyone? So the total kinetic energy for rolling, and that is everything we learning here is for rolling motion. Okay. So for rolling, the total kinetic energy, E total, is E1 plus ER, where VCM, what is VCM? See, if we are going to see in rotation, the speed can be constant. Listen my words very carefully, what I'm saying right now. The speed can be constant, but the velocity at each different point is going to be different. Isn't it? Tell me. Clear na? I'm saying speed can be constant in a circular motion, in a rotational motion, but velocity can be different. Why so? Because velocity is magnitude of speed into direction. Direction can be, you can say I, j, k, and so and so, any particular. So as you can see, if I just stick to this I, so here at that particular point A, or you can say I don't write A now, here that at particular point P, or here at that particular point Q, I is positive here, but I is negative here. So due to direction altered, but speed remains constant. Is this clear, everyone? So which particular velocity we can take to find the kinetic energy in translation motion? So we are going to take this thing, and this thing basically is known as velocity of center of mass. Basically in wheels, or you can say in tires, the center of mass is the center itself, because tires are circular, isn't it? So for a circle, because it's a symmetric body, so center is going to be. But in any case, if any object is doing the rolling motion, which is not a symmetric shape, okay, so some arbitrary shape. So which particular motion, which particular speed you are going to take for a translation motion? So that is nothing but velocity of center of mass. Clear na everyone? For simple symmetric shape, velocity we are going to take for translation motion, for motion in between A to B, which is velocity of center of mass, which is velocity at the center itself. But if in any case the body is unsymmetric, so then we are going to find the center of mass and velocity of center of mass, and that velocity of center of mass we are going to take in translation motion of a rolling. Is this clear, everyone? So then total kinetic energy KE total is going to be 1 by 2 m mass of a body, V square cm, where V square cm, or you can say VCM is square, VCM is the velocity of center of mass of the body. And right now on the previous pages we can find ER is the rotational kinetic energy, right? This thing is rotational kinetic energy, and rotational kinetic energy is nothing but half I omega square. Rotational kinetic energy. Clear, everyone? So in this case, translational energy ET and rotational energy ER does not depend on each other. Obviously they are do not depend on each other, because in one sense we can talk about the translational energy in rolling, in another sense we are talking about the rotational energy in rolling, but everything we are seeing in rolling. So total kinetic energy in rolling motion is what it is, beta, AE total, and that is going to be AE translation. I'm going to write translation, okay, plus KE rotation, R I'm going to write capital R, and that is going to be KE total. Okay, total can be quite good, and that is half m VCM to the power 2 plus half I omega square. Clear na, everyone? One important point also here. Okay, I can draw here. In rolling motion, the velocity of point of contact is 0. What is point of contact now? Okay, just a minute. I can draw and I can teach you in that way. I don't know why it is not. So in each particular kind of rolling motion, velocity of point of contact is 0. So as at this particular point A, the velocity of point of contact means the particular point which is going to be contact with the ground. That particular point at in this scenario A, the velocity of point of contact, you can say in this way, is going to be 0. And VP stands for velocity of point of contact. Okay, so VP, which is velocity of point of contact, is 0 in rolling motion. If it is not, so they are going to slip. Now what it is? Whenever a bike or any particular automobile is going to stuck into a mud or a slippery surface, so the wheel is not going to move ahead. I mean, the wheel is not going to move from this particular. The wheel is not going to move ahead from this particular position S to this particular position T. It is going to spin on its one position. That is only and only rotational motion there, and the wheel and the tire is going to start spin. Clear now, everyone? So in spinning, VP is not zero. So if VP is not zero, so the start, or you can say the tire is going to start spinning. So one thing we can rewrite, okay, yeah, this color. In spinning, in it's PSPI double N. In spinning, VP is not equal to zero. What does it mean? Only rotational motion is occurring there. Only rotational motion is happening there. It's happening there. THEIR or THERE. There. Okay. Clear now, everyone? Clear? So rotational, you can say rolling motion is very, very important in day-to-day life as well as and for understanding part also. Is this clear or not to each and everyone here? Tell me, because next thing is going to be very important. From the next thing we are going to find so many things. Is this clear, everyone, beta? Everyone? Good. So let's see this, what it is. Rolling without spinning. Obviously, only rolling. The body is not spinning at all. Okay, if the object rolls across the surface in such a manner that there is no relative motion of object and surface at the point of contact. As I can write, no relative motion means this spinning is not going to be done and VP is going to be zero. Okay. That is the point of contact. Now, VP, already write it down this thing in the previous page. VP, which is velocity of point of contact, is zero. This type of motion is known as rolling without slipping. Slip is not going to be a single %. So rotation produce translation. So V equals to R omega and alpha equals A equals to R alpha. Okay, what it is? As we all already know, these relation V equals to R omega means linear velocity equals to R radius of a rotation and angular velocity, and linear acceleration is nothing but R into alpha. Alpha is angular acceleration. So this is R. And then the total kinetic energy of a body. Then the total kinetic energy E total EI translation plus rotational and half mv square half I omega square, putting all together the values, the total kinetic energy, and that is going to be the important thing. Okay, total kinetic energy, rewriting everything, every particular single value, I am rewrite this thing 1 by 2 V square R square mk square plus mr square, simple mr square. Okay, and that is nothing but mv square plus half I omega square, putting the value of V, which is this R omega, to make a common thing. Nothing we are doing, you can say wrong here or something which is not, you can understand. Okay, so here if I just take omega square I plus mr square, clear enough. And if I put the value of omega, which is V square by R square, or you can say V by R to the power 2. So V square by R square, and I is mk square and mr square. Clear, everyone? This thing clear now? This one is going to be the important case. This thing. Equation 1 I can rewrite again. Okay, for this rolling motion. So this is going to be very, very important for next few slides. And even in general also. Okay. Okay then. So E total is half M 1 plus K square by R square V square. What it is in general? If I just multiply V square R V square into R, if I multiply this v square upon r square inside this. So what it is going to be? My total kinetic energy is going to be this one. This one is equation 2, and that is also important one. You can say very, very important. Okay. Where EI is translation, or you can say half mv square, and ER is 1 by 2 k square r square into v square, and that is also I omega square. Why so? Because omega is v by r. So if you do this, you can do this, and mk square is I. So I'm not writing anything new, just representing in a different way. So E total, this is also important. You can write this equation 3. So E total means the total kinetic energy divided by the rotation. Okay, this is translation. ET is translation here. Kinetic energy due to translation or due to translation motion. Translation motion. Okay, ER you know everyone. Kinetic energy due to rotation motion. Due to rotational motion. Clear? ET is small t is for translation motion, and small r is for rotational motion, and capital T for total. So 1 k square by r square ratio 1 plus k square by r square. Okay, where k is radius of gyration. Same color, same thing. K is radius of gyration. Is this clear, everyone? K is radius of gyration. Clear, beta, this thing? Okay, now we are going to take this equation 2 to find something new and to correlate. Like what it is. Now this is the Newton's equation of motion for this particular rolling motion. Clear? So where come this v square can be converted into 2gh upon half k square r square. So you don't need to worry anything. Wait. So many pages I need to go ahead. Okay, just wait a minute. I can give you a little bit hint, and then we are going to talk about. We are going to use one diagram, and we are going to reuse this thing again. So just using this diagram, you can understand what it is going on here. Just wait a minute. Okay, so what we were trying to do now here, making energy conservation. Using energy conservation. Okay, using energy conservation. And what is energy conservation? KE total equals to PE total. EE here is potential energy, right? So what is total kinetic energy on the previous page? Where is this? Yeah, this. Half m 1 plus k square divided by r square into v square, right? So if I rewrite this equation 2, so ET is 1 by 2 m 1 plus k square by r square, and I'm going to rewrite mgh. M cancel, so you can, okay, v square also na somewhere. That's what we need to find. So from this we can find v square is gh upon 2gh. So many things I need to put. 2gh upon this value, which is 1 plus k square divided by r square. 1 plus k square divided by r square. Here. So that is the thing we put it here. Initially, if this object, or if this you can say sphere or anything at this particular position, and obviously at this particular position u is, it looks like refractive index, u is 0, initial velocity. Is this clear? So then we can find the acceleration directly. Even we are finding the acceleration in the next another sense also. Is this clear now then? Clear everyone? So this is by Newton's equation, v square equals to u square plus 2as. Third equation of motion, u is 0, a acceleration along inclined plane. So 2as, h you can put s sine theta from this symmetry. So a is g sine theta 1 plus k square by r square, and that is very, very important. What it is? Acceleration of bodies, acceleration of rolling bodies from an inclined plane. Clear everyone? Is this clear? Before writing this thing, let me know it is clear or not. Anushka, I'm talking to you. Yeah, yes. Is this clear, everyone? Good. So then, using second equation of motion, which is s equals to ut plus half at square, we can put t, I mean, we can find t. We can find t in this way, right? Under root 2s by a, and this is going to be the important equation, equation 2. So just putting the value of a, we can get the time also. Putting the value of a is g sine theta divided by 1 plus k square by r square. And everyone know here k is radius of gyration, r is radius of that particular rolling body. It can be cylinder, it can be a disc, it can be sphere, it can be hemisphere, it can be box also. In box we don't have r then. The center point we need to find. Okay, box means this box also. Then what it is? R, the center point. This one, this one, this one. Where the two diagonals going to intersect each other. But you don't get any hard and slow questions like this. Okay. So then you can find this center. Now it is dependent in which way it is going to be rotated. Either in this way or either in this way. But it is not going to be. Don't worry. So this is putting the value of acceleration. We can get time t whenever any particular body is rolling from an inclined plane. Okay, like the previous diagram. So a is acceleration of rolling, v is velocity of rolling, and t is time of rolling. Does not depend on the mass of the object, as you can see. So acceleration of sliding is going to be acceleration of rolling. Velocity of sliding is going to be velocity of rolling. Sliding means they are going to just slip. They are not rotate. Clear? If I'm going to, I cannot show you, but what does it mean? If it is a plane, okay, from this particular plane, just a minute. If this is, if it is a ball, okay, so it is going to do both the motion, right? Suppose this is the center. At this particular, around this particular axis, it is going to rotate in this way and then in this way, right? And then it is going to be translate also. So this is the rolling. Where sliding, you can understand on the perspective of a box, not this color, this. Suppose in the same sense, we have another plane. Okay. In the same sense, we have another plane. So for this particular plane case, if I put a box like this, so it is going to slide. And as a kid, we also slide on the plane like this. So we are going to slide only. Clear? So obviously, acceleration of sliding is going to be more than the acceleration of rolling. Velocity of a sliding is going to be more than the velocity of a rolling. And time of a sliding is going to be lesser. Because obviously, if acceleration, I mean, if in these scenarios, if this one is going to be the higher, this one is going to be the higher, so time is going to be the lesser. Clear? This one is important. Is this clear, beta? Okay. Good. Now moving ahead, special note. If body is sliding on an inclined plane, I mean, if it is sliding, so obviously that is not going to rotate. And if it is not going to rotate, so k square by r square is going to be 0. Means simply, if this case is going to be there, if only sliding, you can see, okay, if only sliding, S-L-I-D-I-N, if only sliding is going to be there, no rotation, only sliding means no rotation. Body sliding on inclined plane means no rotation. So if no rotation is occurring there, so obviously I is going to be 0, that is going to be mk square. So k by r square is going to be, r is not going to be 0. K is 0 here, and that is why k square by r square is 0. And then it is simply v equals to under root 2gh, and a equals to g sine theta, and t equals to 2s upon g sine theta, because s is h. Clear everyone? Clear na? Means if any particular shape or a body like this, so it is not going to rotate generally. Generally, these kinds of bodies are going to slide. Like we are sliding whenever we whenever we are going to play in park or somewhere. So as a kid, right now, nowadays also, kids going to slide on an inclined plane. Okay. I don't think you about, I mean, I can't say about you, but I did this thing in my childhood. And I hope and I believe you also. You are not stuck in your home alone or only glued to your PC or virtual games because of this COVID and after this everything, because of lockdown and so and so. Okay, so whenever you get time, so go into the park. In park, you can see so many physical phenomenon occurring or happening all together. Clear? Seesaw is in this chapter. I teach you like so many. Seesaw now, this you can say sliding, and you can say when this swinging is going to be swing. So we are going to talk about that particular example also. Here, so this is important, and thus when any particular body is not rotating at all together. So this is what we did from, you can say, last 2 slides. This is important table. That is nothing new, but a table to recollect all the data. So for rolling, the velocity is going to be this, acceleration is going to be this, and time is going to be this. If your body is going to be slide only, so the velocity is going to be this, acceleration going to be this, and the time is going to be this. If rolling or sliding, we cannot say, so that is going to be velocity is this, acceleration is this, and time is this. Okay. Nothing new, but summary from the last 2 data. Important one. Okay, this one is very important. This one is also this one. This one, this one, this one. This one also important. This one also important. This one also. Okay. Even if you just forget about the slide, the last one, but the upper 2 is very important. Moving ahead, the various forces acting on the rolling body. Like I already given you this diagram. So we are going to talk about this diagram, and we are going to find the coefficient of friction, this mu. Okay. So what it is, rolling motion, the various forces acting on the rolling down a body are the weight mg of the body in the vertically downward direction, normal reaction force n of the surface of the plane on the body which acts normal on the inclined plane, the force of friction which acts opposite to the direction of motion of a body. So what it is, this equation is mg sine theta minus friction force is going to be ma acceleration, or here acceleration we are going to use for the rolling. And okay, now on the next page you can see if it is the mass, so in this particular downward component we have a mg, and due to this plank and due to this inclined theta angle, this weight is going to be redistributed in 2 directions. This is your mg sine theta component, or you can say perpendicular component, and that is going to be horizontal component. And we know the natural force or this normal force is always perpendicular to the plane. So plane here is this. Okay. So mg cos theta is take care of this, but we need to find the motion and acceleration in this direction. So in this direction we have net force, which is rolling acceleration. So that is MA. Okay, AR you can write. And in the backward side, we have mg sine theta minus friction force. Clear? Because frictional force is, as you can see, this arrow is going to be in the backward side. So this is the equilibrium of your force in the vertical direction or along the plane, along the inclined plane. So that is mg sine theta minus friction force equals to this. We know F, frictional force, is mu n. Clear, everyone? And from this diagram we can see that n is what? Mg cos theta. N is mg cos theta. Clear? I can remove this. So in this way we can find this mu. Mu is what? Coefficient of kinetic friction. Coefficient of friction. You can write kinetic or static, any kind of thing. Coefficient of friction. Here, beta. So we are going to find the coefficient of friction with this mu. So this is simply mu mg cos theta, mg sin theta, k square by r square, 1 plus k square by r square. Basically, this is going to be there, and mg sin theta is going to be taken as a common, and we do this calculation all together. So mu is going to be tan theta 1 by r square plus k square, and that is important one all again. Okay. And for disk, as I already tell you, for disk and cylinder, k square by r square is 2. How so? See, for disk or cylinder, I have, this is 1 by 2 mr square, and that is mk square. So beta, r square by k square, I can get 2. Clear? This r square by k square term. So the condition for rolling motion of the cylinder along the inclined plane without slipping is this. What it is? Means if my coefficient friction is not equal or greater than the 1 by 3 tan theta, so it is going to slip. And what is the condition for slipping? Condition for slipping is Vp, velocity of point of contact, is not 0. So basically, the cylinder or disc is going to slide more. Okay, this equation teach me if, okay, what it is, equation B you can write. So from the equation B, what we can understand, equation B gives us, not this. If mu is not equal and greater than 1 by t tan theta, then what happens? Then the body starts sliding or slipping. Then the body, instead of body, I can write disc, because we are talking about disc or cylinder. Okay, cylinder I can draw. I cannot write cylinder. You can understand. So the disc, then the disc or cylinder can start sliding instead of rolling. Is this clear, everyone? Means if mu is equal and less than, not equal. This is the correct. Means if mu is lesser than this 1 by 3 tan theta, so then the disc is going to slide. It is not going to roll. Clear, everyone? Because r square by k square is 2 for disc, and if the disc is, if this condition is not going to fulfill, if the coefficient of friction is not equal and greater than 1 by 3 tan theta, so instead of rolling in this way, the body, because it is like look like a cylinder also, so from this plane it is going to slide directly. It is not going to roll. Got it? And you can see my palm doesn't give this condition, so it is going, even it is going to rotate. Where is my hand? Yeah, you can see that it is going to rotate, not slide. Why so? Because this condition is fulfilled. Okay, so this is important one. If this condition is fulfilled, so what you can see, the rolling, if it is not fulfilled, if you can have your this mu, which is what it is, coefficient of kinetic friction, so then the disk and slide can start sliding. Vp is not zero there, and Vp is zero, which means the body is rolling. Rolling is rotational motion as well as translation motion. Clear? And that is, I give you in the last class also, important, you can say analogy or relation between translation or rotation. So translational inertia is mass. Okay, this is basically, this is for translation motion. This is for translation motion, and that is for rotational motion. Rotational motion. Clear? And we know and we discuss about this in the previous also. So in translation motion, translational inertia is mass. In rotational inertia, rotational inertia is mi, moment of inertia I. Here you can see that linear momentum P equals to mv, angular momentum J equals to I omega. Okay, this one, work done, force into displacement, and for varying force, F dot ds. This is torque tau constant, and tau into theta, and for varying tau, d omega t d theta. Energy half mv square. Okay, this one is half mv square, half I omega square. Force into displacement, sorry, force into velocity, which is power, torque into angular velocity. So these are the analogous, or these are the changes you can see all together for translational motion and rotational motion. Is this clear, everyone? On the next page, we have 2 points also, which is work energy theorem. W equals to half mv square minus half mv square, and work energy theorem in rotation motion. So this is translation. I'm going to write translation, not motion, and that is for rotation. Okay, 1 by I omega square minus I naught omega square. I naught is initial angular velocity and omega is final AB, angular velocity. Rotational impulse, change in momentum, angular momentum, linear impulse, change in linear momentum. In this way we can finish this, but you need to do this. Okay, do that. A solid disk of mass m, 16 kilogram, and diameter r is also given. It is free to rotate about its own axis. Find out required torque that would increase angular velocity from this 120 rotation per minute in 8 seconds. What you need to find? Required torque that will increase angular velocity. Okay, do that. Use the equation torque tau equals to I alpha, and use alpha equals to omega final minus omega initial into divided by time, where omega you can write 2 pi f. F is frequency. Okay, as a hint for you guys, torque tau equals to I alpha, alpha beta omega final minus omega initial divided by time. Omega is 2 pi f, because this is your frequency. Okay, 120 rotation per minute. You need to find rotation per second. Do that and tell me the answer. And then we have one more question. You need to do that also, and then you need to attempt this class assessment as well. Do that quickly. I already give you enough hint for completing this. Is it done or not? How can you do that? I mean, why you are taking that much time? Yes, yes, yes. Option C is correct. 5 by 4. See how you can do this. The students who are struggling to do and don't get it still, torque tau equals to I alpha omega f minus omega I by t. As you can see, I into 2 pi nf minus ni by t, I equals to mr square. And we know everything is given, so I we can find, m is given, r is given, right? So we can find this. Okay, now 2 pi omega final, which is 120 upon 60 into 8, because this rotation per minute, rotation is given per minute. So first of all, we need to find for this second and then divided with the time, which is 8. Got it? So you need to solve this and automatically you can get the answer in pi form, which is C. Clear everyone? Is this clear to you, Kanishka? Or Mukeshwaram, or this Bhuvana, or this Anushika also? Clear everyone? Okay. Next one. A solid sphere is in pure rolling motion on an inclined surface having inclination theta. What is the perfect answer? I mean, which particular option is correct? Frictional force acting on a sphere is F, mu mg cos theta. F is dissipative force. Frictional force, friction will increase its angular velocity and decrease its linear velocity. If theta decreases, friction will increases. Which one is the correct? Just a minute ago, I give you this. Okay. See, in this, it can be MCQ, MSQ also. A can be correct and C can be correct. But in this case, C is going to be given. Frictional force acting on the sphere, as we can see for this particular thing, mu n. Here, mu n. And for this inclined plane thing, if it is mg, so that is going to be mg cos theta in this n, and here it is going to be mg sin theta. Clear? But the more accurate option here is this C. Friction force will increase its angular velocity and decrease its linear velocity. How so? In this way. In case of pure rolling, friction, okay, mg sin theta, okay, wait. Only this is not going to be in pure rolling case. In sliding case, in normal case, you can see that. But in pure rolling case, we have the frictional force formula, that is mg sin theta 1 plus mr square by I. Okay, 1 plus mr square by I. So, beta, from this relation, F is directly proportional to sin theta. Clear? So, therefore, theta increases, force of friction will also be decreases. Because if theta decreases, so sin theta value is going to be decreased. Because sin theta is initially half, then 1 by root 2, then root 3 by 2, and then 1. Clear? Near to the 0, sin theta is going to be 0. So in this way, we complete this lecture as well as the chapter. In this particular lecture, in this particular live session, we complete kinematics of rotation motion about a fixed axis, dynamics of a rotational motion about a fixed axis, angular momentum in case of rotation about a fixed axis, and conservation of angular momentum and rolling motion altogether. Now, as usual, this is a test assigned to you. You can click on this particular link and there is a test for you guys. Okay, class assessment test link. So this is your class assessment test link. Open that particular link, try each particular question from there and let me know if you are stuck in anywhere. Clear beta? Meanwhile, you can go through and I'm opening your this class assessment, and as you know, homework is important too. Okay, you need to do that also. Complete that also. Tell me everyone, the test is visible or not? Meanwhile, I need to open your test also because I don't know what particular questions we put it. This is this. Okay, there are 6 questions and opt all of the 6. I mean, try all of the 6 questions. And if you find difficulty in any one of them, so you can ask me out. But I think every particular question I give it to you. A particle of mass m, 10 grams moves along a circle of radius, which is a constant tangential radius acceleration. If the kinetic energy of the particle becomes this, by the end of second revolution, after beginning of the motion. Okay, what is the magnitude of acceleration? Nice. So initially I will find the v square. Okay. Tell me any particular question if you are facing difficulty in understanding and that is not clear to you. And if it is not, so you can do that. And if you want to discuss any particular question, so let me know. Okay. We have still 5-6 minutes. Is this clear, beta, everyone? Hello, hello, hello. Am I audible? Am I visible with everyone? Okay, test is visible now, everyone. One thing I can do, I can write the question number and correct answer, or you can say correct option. You can match it. And if you feel any particular question you are not understanding, you can ask me in the next lecture, which is class assessment. Clear? Not. Is this clear with everyone? Because seeing you makes me more sleepy now. Even I don't sleepy at that moment, but I can be after seeing you long time. Tell me, is this clear, everyone? I need to check also. The first is A, second is D, third is B, A, D, B, A. Okay, so that is A, B, B, A. These are the correct options. Okay, A and then A and then B. Wow, so many A's. A and then B. A, D, B, A, B. Exactly. So this one is the correct option for you. Okay, from the given thing, you can do and match it up. And if you don't find any particular same answer, so you can ask me in the chapter assessment. Clear, everyone? Okay.